In this lecture, we will look at a few characteristics related to MOSFETs specific to integrated circuits. Now, what do we understand by integrated circuits? You basically have a single substrate on which several different circuits are grown, and they are always tied together on the same chip. Now, what we know for integrated circuits is that if you have two devices that have the same dimensions and are of the same type, they are nominally identical. What does that mean? If I take two devices, let us say two MOSFETs, and I apply the same gate source voltage to them, and I apply the same drain voltage to them, they will have exactly the same current. They will have exactly the same current. That is what we mean when we say that the device is nominally identical. They will have the same characteristics. Similarly, if I take two resistors and they are of the same type of resistors on the integrated circuit, I use the same material to create the resistor. Remember that a resistor can be created in many different ways on an integrated circuit. I can use a piece of polysilicon, I can use a metal, I can use a lightly or strongly doped resistor, a strongly doped piece of silicon. There are many different ways to create resistors. If I build a resistor using a certain width and length of material on the integrated circuit, if they have the same dimensions, I will assume that they are nominally identical, they will have the same value of resistance. What I cannot guarantee is that if I take two different ICs and I have the same dimensions of MOSFET or resistor or capacitor, I cannot guarantee that on those two different ICs they will have the same value. This is because the two different ICs may be processed in very different ways. Maybe the temperature of the furnace in which the substrate was baked was different, or maybe the doping concentration was slightly different, etc. The actual value of device parameters such as resistors, capacitors, capacitance value or threshold voltage, the doping concentration, etc., or the thickness of the oxide, all these things vary with the process. In other words, they are different for different ICs. Similarly, the value of Vt or mu n or the value of the resistance can be a function of temperature. If temperature increases, if the resistance has a positive temperature coefficient, the value of the resistance will also increase. What I am assured, however, is that if the two resistors are on the same integrated circuit, they will experience the same temperature change because they are so close to each other, and they will therefore experience approximately the same temperature change. So, in other words, what I am assured of is these devices will be nominally identical, they will experience identical variations. Similarly, what you can also tell is that ratio of quantities, okay, will also be fairly constant. This is because, for example, with temperature, if R1 and R2 have the same temperature coefficient, if they are made with the same material, then R1 by R2 will stay constant over temperature. How is the device made? If I were to draw the cross section of the device, if I look at the MOSFET, I need the two drain source diffusions. I will take the example of an NMOS transistor, so there will be N plus diffusions on the P substrate. I will denote that by P sub, and I will grow the gate oxide, and on top of that the polysilicon will be the gate. So, I will denote these by these three, the gate, drain and the source. Please note that the device clearly has a fourth terminal, which is the bulk terminal. So, now we introduce the concept of the MOSFET being a 4-terminal device. I will denote that by B. Normally, all NMOS devices on the same substrate will have a common bulk, and to ensure proper operation you need to make sure that these diodes are always, these PN junction diodes are always reverse biased, and therefore, the P substrate is always connected to the lowest potential on the integrated circuit. We will assume that we are working with unipolar circuits, and therefore, the lowest potential circuit is ground. So, the substrate terminal is not under your control, it is always connected to ground. If I take such a device, when I connect the device in the common source amplifier configuration, then clearly the bulk to source voltage is 0. Now, it turns out that if the bulk to source voltage were not 0, the threshold voltage of the device will change. That can be represented in this form. If you want to know more about this, please consult a good devices, semiconductor devices textbook on MOSFETs that will explain the exact dependence of threshold voltage on the source bulk voltage. I will just give you the final result. The actual expression for the threshold voltage is Vt naught, which is the threshold voltage when the source bulk voltage is 0, plus some factor gamma times the Fermi potential plus Vsb Please note that if the source bulk voltage is 0, then Vt will be Vt naught. So, for the common source amplifier, the threshold voltage of the device is Vt naught. Now, also note that the bulk is always connected to the lowest voltage possible, therefore, normally the source bulk voltage is positive and the threshold voltage would be larger than Vt naught if the source is biased at a larger voltage. There are many circuits where this would happen. I will show you what will happen if we look at the circuit which you folks would have seen before, which is the cascode amplifier. Please note that the source bulk voltage for M1 is 0, but the source bulk voltage for M2 is not 0, it is larger because the source of the transistor will have a voltage of VB2 minus VGS2. Since VSB2 is positive, Vt2 is greater than Vt naught, the two devices will have different threshold voltages. So, any circuit where the source and bulk are not connected together will have this effect. Now, there is one more thing to keep in mind. The minute the source and bulk are not connected together, we should also look at a different aspect of this particular effect. Please note that the bulk is connected to ground, which is the lowest potential. So, normally the bulk is always at small signal ground, whereas the source voltage need not always be at small signal ground. For example, the source of M2 will experience a signal swing. We need to quantify the effect of this. Clearly, there will be a signal aspect to this. We will represent that by a small signal conductance, a transconductance called GMBS. I will represent that as GMBS, which is nothing but dou ID over dou VBS. Clearly, this is the dependence of ID on VBS is through the threshold voltage. So, therefore, this is dou ID over dou VT times dou VT over dou VBS. And now, we need to calculate these two quantities. Let us look at dou ID over dou Vt. So, ID is clearly half mu n C ox W over L into VGS minus Vt the whole squared. Now, please note that dou ID over dou Vt is the negative of dou ID over dou VGS, which is nothing but minus Gm, where Gm is the transconductance of the device. What about dou Vt over dou VBS? Dou Vt over dou VBS is clearly minus half gamma times this expression. This is of course calculated at the operating point. So, VSB value is chosen to be the DC operating point value to calculate this expression. Therefore, I am going to call this some factor k, because GMBS is finally minus k times minus Gm, which is k times Gm. If I were to now draw the incremental equivalent circuit of the device, I have the transconductance of the device Gm times VGS. I have the small signal RDS of the device representing the dependence of ID on drain voltage. Finally, I have a third incremental voltage controlled current source, which is simply GMBS times VBS, where the bulk terminal is connected to small signal ground. So, if the source moved with respect to bulk, you will have a third small signal component in the small signal picture. Now, the good thing about this is that normally k is less than 0.2, so that the effect of GMBS is one order of magnitude 0.2 or 0.1. So, the effect of GMBS is one order of magnitude lower than Gm. So, in many cases, even if the source were to move, for hand calculations the accuracy may not be lost if GMBS is ignored. But this is definitely something to keep in mind, because once you go to a simulator, you will see this difference. So, this is one of the second order effects to keep in mind when you are designing amplifiers with MOSFETs. Now, the same thing is valid even for PMOS transistors. So, PMOS transistors will also have the same effect, they will also end up having the same small signal equivalent circuit. So, with that we will assume that the most of the small signal effects in the device are taken care of. So, the low frequency model of the device that we will look at will consist of the three quantities GM, RDS and GMBS.